Awesome. So Bernardo, thank you so much for joining us today. I'm super excited about this. Today's topic is kind of hitting all the marks in terms of being mathy and also FM and also aesthetically pleasing. So we're excited to have you. And I'll just go ahead and let you take the stage. Thank you so much.
Awesome. Yeah, thank you so much for the invitation. I'm really glad to be here. And as you're saying, I guess my goal for this talk is sort of um to convince folks from either side. So if there's a very mathy person, I guess what I'm trying to convince you about is that you could potentially use some formal method things to help you out in your math. And if you're a very formal methods person, then I guess what I'm trying to convince you about is that maybe you could apply your cool formal method techniques to some math problems. So that's sort of, I guess, where this is situated. So that said, I'll just hide the Zoom controls and get started. Okay, so I'll start by talking about standard graph coloring. So in standard graph coloring, what we want is a function from the set of vertices to integers, let's say from 1 through k, such that if two vertices get the same color, then their distance needs to be greater than 1. This is one way of formulating standard graph coloring. So for example, if we have this path on 4 vertices, let's say the first vertex gets 1, next one cannot get 1, so it gets 2, then the next one gets 1 again, and the last one gets 2. So now I'm going to talk about packing coloring, which is the kind of coloring this talk is about. So it's also a function from the vertices to the integers, but the requirement is a little bit different. Now, if they share the same color C, their distance needs to be greater than C. So in the standard coloring world, the requirement is always that the distance is greater than 1 if you share color C. Now the requirement of distance is based on the color. So if we start putting a 1 here, then I'll put a 2 here because that's allowed. Now notice that my 2 ones are fine because they're distance 2 from each other, but now I could not put a 2 in the last position because it would be a distance 2 from it from another 2. So I need to put in a 3. Does that make sense?
Yeah, totally.
Okay, beautiful. So let's do a couple more examples because if I fail to convey how this notion of coloring works, then the whole talk will be a bit hard to understand. So, so let's go and look at some infinite graphs to see how this same notion applies. So if I have now the infinite path, then I can start by coloring with 1 and 2, then a 1, then a 3. That part we already saw. And now I can place a 1 again, a 2 again, and more in general, I can continue with this pattern of 1, 2, 1, 3, 1, 2, 1, 3. So notice now that if you look at 2 occurrences of the number 3, they're a distance 4 apart, sorry, from each other, and that's fine because 4 is greater than 3. So what this means is that if we consider this infinite graph, its packing chromatic number, so the minimum number of colors to make it work is 3, right? And this graph, I write it as the Z graph because you can identify it with the integers where 2 consecutive integers have an edge.
You're not allowed to have a 0 color though, right? Because that would make the problem.
No, exactly. That's exactly right. So I'm starting from 1. And later on, maybe if we've had time, we can talk about generalizations where I don't give you all the colors. So let's say I give you 2, 3, 5, 7, 9, 11, for example, or some other set that's not the colors from 1 to 3. And what you could do with those, it's also an interesting question. But from now, for the beginning, it's just 1, 2, 3, 4, and so on. So now consider this graph. So it's like a sort of ladder, like an infinite ladder kind of thing. So I can start placing a 1 here. I cannot place a 1 in its adjacent neighbors, but I can place a 1 diagonally, and so on, right? So with this sort of coloring of the ones, I've colored half of the graph. So that's pretty good progress. Now I can place a 2 here. I cannot place a 2 in immediately down left or here, but I can place it here, right? Because that also respects distance. And so by doing that, I can sort of place 2s in this pattern. Then when I place a 3 here, I can place the next ones like so. Those are distance 4 from each other. And then I can place those 4s there and 5s there. And you can check this pattern sort of continues well, and it allows me to do this infinite ladder with 5 colors. So what we're proving here is that 5 colors is enough. Not exactly that it's the best number, right? Maybe there's a clever way of doing this with 4. So the question now is whether we can do better than this. So yet an even more interesting example, in my opinion, is what if you have now the entire grid? So we went from the path to sort of the infinite ladder, and now full two-dimensional infinite grid. And the answer to this question is 15. And that's basically all what my talk is about and how we got to that number. In particular, using set solving. I guess that's the formal methods aspect. So let me now give a little bit of background on packing colorings. So they were proposed by Goddard and others at Clemenson in 2002, so over 20 years ago. And the original name was broadcast coloring. So they were inspired by some radio notions. And then in 2007, Drescher and others reinterpreted this notion and thought about it in terms of packing. Because of time, I'll not go into details of the namings, but since then, over 70 papers have been studying different aspects of packing colorings over different graphs, asymptotics, concrete examples, and so on. So the latest survey by Drescher and others states that the most important open problem with respect to infinite graphs is to find the packing chromatic number of the infinite square grid. So at that time, 2020, the problem was still open. And my talk is based on my work with my wonderful advisor, Marijn Heule, on how we prove that the answer to this question is exactly 15. So that's sort of the secret number of today. So let's talk now about a bit of the historical progress on this question, because we didn't do this from scratch by any means. So this is sort of a plot over time of how the bounds were sort of advancing. So at the very beginning, in the seminal paper, people knew that the true answer was between 9 and 23. Then slight improvement on the upper bound to 22. Then slight improvement on the lower bound to 10. And then 2010, I guess, was a wonderful year for packing colorings because that's a big improvement on both sides. So now the answer is between 12 and 17. And then Martin and their group move it to 13, 16, then 13 and 15. And now a few years later, we started working on this problem. In 2022, we moved the lower bound to 14. And then finally, 2023, this year, over 20 years later, we have finally connected the lines at 15. And something I want to remark on is that from 2015 onwards, all the progress on this problem was done through SAT solvers. So at the very beginning, it was more, I guess, like traditional pen and paper math. Then there were some simulated annealing algorithms, some backtracking. And then it seemed that the best tool ended up being SAT solvers. So in order to get started with the real issue here, how did we do this? Let's start talking about how we can use a computer at all to prove anything about an infinite object, because that sounds a bit weird. So there are several, I guess, considerations here. One is whether you're proving a lower bound, so that the true number of colors is above a certain amount k, meaning that k is not enough, or an upper bound, meaning that k is enough. So the techniques are going to be pretty different. So if you're going to prove that k colors are not enough with a computer, then probably what you want to do is the following. It's to find some finite subgraph h of g, and then prove that that finite subgraph cannot be colored with k colors, that k is not enough for that graph. And then, the conclusion is that if it's not enough for the subgraph, then of course it's not going to be enough for the whole graph. For upper bounds, then we get a second separation. Because for an upper bound, we need to show that it is possible to color these infinite objects. And to color infinite objects, basically, you can think of colorings as either periodic. So it's like the ones I showed earlier, for example, where you show how to do that. And then you say basically, oh, and I can repeat this forever. or aperiodic colorings in which there's not a pattern that you're repeating, but somehow you're able to always keep finding colors within the appropriate range from 1 to K. So if you want to find good aperiodic colorings with a computer, then the theory is really not great. We really don't know how to do this well. And if people are interested, at the end, we can talk about some concrete open questions about this that I would love for somebody to find an answer. And for periodic ones, the main idea is going to be using something that we call toroidal edges that will encode in a finite subgraph H the fact that I want to use that subgraph periodically for the full coloring. So I'll add some extra edges that I'll sort of make the graph understand that I need a coloring that takes into account the fact that I'm going to connect it with itself periodically.
Bernardo, do we have any kind of result that says that if a aperiodic solution exists, then a periodic one does, or vice versa? Or are they distinct?
I mean, yeah, that's a fantastic question. If somebody has the answer, I would pay to know that, because I can talk a tiny bit about it. I know, and the proof is not hard, that this is true for one-dimensional colorings. So by one-dimensional, I mean the graph is one-dimensional. So if we talk on the graph Z, for example, and I give you some colors, so not necessarily from 1 through K, but I give you 2, 4, 5, any subset of the natural numbers. If I give you those and they're able to color it, then they're also able to do it periodically. And that's not hard to show in general. You can either show it by some pigeonhole cute proof, or it's a consequence of some deep results, or not deep results, but on some theory of finite subshits.
Right.
But if you try to do that in 2 dimensions, then completely breaks as a technique, because we know that in 2 dimensions you can have aperiodic, like inherently aperiodic objects like Wenck tiles and so on. So we really don't know. Therefore, we also don't know if I give you a set of colors and the infinite square graph, whether it's decidable if you can color that or not, because periodicity is very related to decidability.
Yeah, that's super interesting.
So we can
sidetrack. It's just, it reminds me of like omega regularity with linear temporal logic, right? Where if a counterexample exists, then an omega regular counterexample exists, which can be represented finitely because it's a prefix plus a repeated postfix. And so that's essentially like that language has one of these equivalences, and it seems like it'd be useful if you had that here, but obviously you agree, like it would be useful. And
no, that sounds amazing. I'm actually not aware at all of the temporal logic sort of super was it called, sorry, super regularity?
It's omega regular.
Oh, omega regularity. Okay. Yeah. So it could be interesting to see if there's for example, it's not too hard to see that you can encode this coloring in first order logic. That give you some capacity ideas, but yeah, we can talk about that later. It's very interesting. I would die to know whether it's true or not that in this particular problem, an aperiodic coloring implies a periodic coloring, and I really don't know the answer yet. Okay, so let's do an example. So if we consider again the one-dimensional integers, and the answer is 3, as we saw earlier, the way you would prove this with a computer looks like so. So first you need to prove the lower bound, so that 2 colors are not enough. And for that, the path on 4 vertices is enough. If you try to use colors only 1 and 2, you will end up very sad at that smiley face, because it's just not going to work in any combination. To prove the upper bound, meaning that 3 colors is enough, a way you can do this with a computer is by adding these toroidal edges. So you're sort of closing this path into a cycle to represent the fact that you will extend its coloring periodically. So notice that the packing coloring here, 1, 2, and 1, 3, works even when I add this extra edge right now between the first and the last vertex. And that implies that I can sort of do one step of unrolling my coloring like so. Why does it imply it? Well, because we know from the coloring on C4 that it's legal to have the first 4 vertices be 1, 2, 1, 3. And now I know that it's legal to put the vertex on the right of 3 be a 1, because of the toroidal edge on C4. And because of that same edge, I know that it's fine to put a 2 on its right, a 1 on its right, and then finally a 3. And so the colorability of C4 implies that of C8, and so on and so forth. So this sort of idea is enough to prove this upper bound on the one-dimensional integers. So now, what are the good subgraphs? Because I showed you that that P4, the path on four vertices, was good for a lower bound, and C4 was good for an upper bound. But what are the good finite subgraphs for Z2? So when Eckstein and their group prove a lower bound of 12, they use the 9 times 15 grid. Martin and their group, for proving a lower bound of 13, use the 14 by 14 grid. What we use is slightly different. We use the D14 diamond. And part of the reason for this is that our intuition tells us that given we're in Manhattan distance, this is the circle in the Manhattan distance, and there's some intuition of why that makes it a better shape to prove lower bounds. So from now on, I'll represent the subgrids like so. So without the vertices, just with cells, but you need to bear in mind that they're connected only to their orthogonally adjacent neighbors. So the first step towards obtaining our result is the use of translational symmetry, or in layman terms, what I like to call it just forcing the center. So Exon and others approved a lower bound of 12, and they assumed that the vertex 5, 5 in this finite subgrid would get color 9. What we do is to assume that the central vertex in the diamond 14 will get color 6. And let me explain why it's fine to assume this. So first, I guess the center is the best vertex to force. If you're gonna be assuming the color of some vertex, you might as well assume that of the center because it's the one that participates in the most clauses. I guess I haven't talked about which clauses, but what we mean by that is in the most number of constraints. If you have a vertex that's at the very edge of this finite subgraph, it has sort of fewer total neighbors at the different distances. A more formal way of saying that, I guess, is that if you want to consider the different balls of different radiuses centered in some vertex, this is the vertex that sort of captures the most. So why is it fine to assume that we will have color 6 in the center? Well, so first, we know based on our previous work from 2022 that there's no solution with 13 colors. So what that means is that if there were a solution with colors 1 through 14, but not using 6, then we could map that solution to only use colors from 1 to 13, right? Because basically, higher colors are more restrictive than lower colors. So if you have a solution with colors 1 through 14 avoiding 6, then you can map it to 1 to 13, because both are using at most 13 colors, and the one on yellow uses colors that are harder to use. So for example, if we had this solution here on the left, we could map it to that on the right by changing the 14 to a 13 and so on. The 7 changes to a 6, and we know that that's fine because the 6 was not being used before. Does that make sense?
Yeah.
Awesome. So notice that the 1s, 2s, 3s, 4s, and 5s, I'm not changing it from left to right because those are common to both. But everything that's from 6 and onwards, I'm shifting 1 down. So therefore, a solution, if exists, must use color 6. And now the idea is that we can safely assume that not only it uses color 6, but it will use it at the center of our finite subgraph. Why is that? Because if it uses 6 somewhere, I can just sort of choose to translate the finite subgraph I'm looking until I situate it at a point where 6 is at its center. So if X is this infinite solution and it uses 6 somewhere, I can try to imagine how the D14 centered in one of the 6s that it uses looks like. So a natural question, if you're gonna force some color, is which color is best? And we did some experimental analysis on this, and it turns out that 6 is the best color. So this is the runtime to prove a lower bound of 14, which is a bit easier, because doing experiments with 15 is way too expensive. But we did this experiment with 14, and 6 is the best color to force. And there's some intuition. If we have extra time, I can talk about why some color roughly in the middle is good. So now let's go to the center of our business, which is about encoding this in propositional logic, so then we can use a SAT solver to find the answer. So we want to encode in propositional logic the fact that the chromatic number of dr, so a diamond of radius r, is at most k. So the first step is that we will just use the natural variables, so representing that a vertex v will take color c. So we will call those just xvc. Then we need to enforce that we actually get a coloring out of this whole thing. So we need to enforce that for every vertex, at least one of the colors will be chosen. So that means that we get a clause per vertex. We call this at least one color clauses. So if the radius is r, given that the number of vertices is roughly r squared, you get r squared clauses here. And now we need, I guess, the most important clauses, the ones that encode the packing chromatic restriction, which are simply that if U and V are at most distance C, then just they cannot take both color C. So one of them must avoid that color. That's what this junction is expressing. And the number of clauses here is basically as follows. So for each vertex, which is counted by the size of the R, you need to avoid everyone in its radius C. So that's DC many vertices, and you're doing that for each color C from 1 through K. So that's asymptotically, R squared K cubed many clauses. And then finally, we do add this center clause to force the color of the center, which is one clause and I guess O of 1. So the total is of course dominated by the at most one distance clauses, which are of R squared K cubed. Can we do better? Well, of course we can, because that's the title of my slide. So how can we do better? So the direct encoding was using so many variables and way too many clauses. So what we need in order to prove the lower bound of 15 is to set the parameters R and K to 14, which results, if you plug in the numbers, to roughly 1 million clauses. And the bottleneck is, of course, in the distance clauses. So in our SAT 2022 paper, we propose a recursive encoding that uses R squared K log K clauses only, but it is mainly a theoretical contribution because the constant hidden in the asymptotic expression is actually pretty large. It's like 64. And it actually doesn't work much better than the direct encoding in practice. So in this new work, in order to get our results, we present a practical encoding that works really, really well. And this is probably the main contribution of our work. So let's see how it looks like. So how do we do the class encoding for encoding that you can pack in color dr with k colors? So the first step we did was some reverse engineering. So there's a pre-processing tool that's called BVA. It stands for Bounded Variable Addition. And what it does is that it takes a CNF formula and it tries to re-encode it to reduce the number of clauses. So if there's a way to re-express your same Boolean formula with fewer clauses, this tool will try to find it. And we did that over our problem, and it actually did substantially reduce the number of clauses, which was very interesting. But when we put the new reduced formula into a SAT solver, the solution times didn't improve. So what we did was to reverse engineering this tool to understand how it was sort of automatically, by doing some greedy heuristic choices, how is that it managed to reduce the number of clauses and then inspire an encoding based on that. So the main finding is represented with this example. So we found out that BVA is introducing something that we call regional clauses. So instead of thinking of the color of a vertex, it's sort of a way of thinking of colors of regions of a graph. So it'll create a new variable y1 that represents that one of those 3 vertices has color 4. So it's now a variable that represents that somebody in a particular region gets a particular color 4 in this case. This second new auxiliary variable y2 is doing the same, but now over this square. So both variables represent that at least one vertex in the region gets color 4. And the question is, well, why the heck is this useful for anything? So it's actually pretty cute, in my opinion. The reason why this improves the encoding is because now we can say that at least one of them must be false, right? Because I cannot have a 4 in both regions, because if I do, then they're necessarily going to be a distance at most 4 from each other, which is going to be a conflict, a problem, right? So we can now directly say that at least one of those regions must not receive color 4. And therefore, what's happening there is that, oh, sorry, I just, one thing before that. Therefore, what's happening there is that I'm avoiding to sort of create a clause for all the possible pairs. So saying like the first vertex in the first region and the second vertex in the second region cannot be both 4. I'm now doing it all at once by saying that the 2 regions are sort of incompatible. So the problem of why this, if you just use this automatic BBA tool, doesn't work well in practice is because it creates different shapes of regions and places them awkwardly in the graph. Because it's a greedy and a heuristic tool, it doesn't really have a knowledge of how to do this in a structured manner. So the main idea of the plus encoding is to use this regional idea, but use it in a structured way by using this, we call them plus regions because they look like the plus symbol, but it's just a diamond of radius 1, if you want to think it that way. So that's how one of the plus encoding, the plus regions look like in that particular diamond of radius 6. So we place them in this structure and symmetric manner, and that's going to be quite important. So just an example of the benefit we get out of doing this is that, as you can see, the number of clauses from direct goes way down to what the automatic tool does. By doing the plus regions, we increase the number of clauses, but our solution time is dramatically better, both on the direct one by a factor of 10 and even by a factor larger than 3 over the optimized formula itself. So another key step in our solution is symmetry breaking. So the idea here is that we will exploit the inherent symmetry of our finite subgraph. So if we have one of these diamonds, this is the 6, for example, I can rotate it over that line and it's still the same. I can also do that over that symmetry and it's still the same. And I can also use this symmetry and it's still the same. So that gives me an 8-fold symmetry. And a problem is that if you just place the plus symbols in the way we were thinking, you actually break one of the symmetries. Now it's no longer symmetric with respect to one of the symmetries, and you can only get a 4-fold symmetry using the plus encoding. But there's a way to fix this. The idea is to break the symmetry of the problem before re-encoding using the pluses. So how do we encode this symmetry breaking? The main observation can be illustrated with an example like so. If you consider a sub D5 of your finite subgraph, because of the constraints, there can be at most one occurrence of number 10 in this finite D5. So we can enforce it to appear in a particular region, so in the sort of north and east region, because we know it can appear at most once. And if it were to appear somewhere else, well, I could just pretend to rotate it so it's placed in the region I like. So the way we do this in logic is simply by adding negative units on the positions that are not in my preferred region to forbid that those will get colored with 10. And if for some reason there were to be a solution that doesn't use any 10s in the central sub D5, then we can break symmetries on the 9s when considering the sub D4 that's around the center. So that's the main idea of how you encode this. And next ingredient of our solution is called cube and conquer. And it's a very general divide and conquer paradigm for SAT solving. It was introduced by my advisor about a decade ago, and it goes like so. So you have a CNF formula phi to start, and you need a tautological DNF. That's just a disjunction of cubes. That's where the name comes from. And the reason why this, or the sort of main equation of cube and conquer is the following. The satisfiability of our formula bar phi is equivalent to the satisfiability of their conjunction, because phi is a tautology. And that's equivalent to whether var phi in one of the cubes works. And that's actually progress already. Why? Because when you have these M-independent problems, you can just solve them in parallel. So this is sort of a way of thinking of dividing your problem and condition your solution on these CI cases. Each of those is a case, and you're saying, okay, is my formula true if I assume this case or if I assume this case? And given that the original phi is a tautology, that means that it's a complete partition of all the possible cases, and therefore that equation is right. So the intuition you want to think is that this formula phi is composed of these cubes that are an exhaustive split of the problem into cases. So the question then is how these cases would look like. And that's actually a very important question, because the whole performance of cube and conquer will be determined by how do you split your problem into cases correctly. So if you have too few cases, then you weight parallelism. And then if you have too many cases, then you waste the power of a SAT solver. So for example, if your formula has n variables and you have 2 to the n cases, then sure, each case is trivial, but then you'll solve 2 to the n of those, right? None of those use the practical power of SAT solvers, and therefore you completely wasted CTCL. You also want your cases to be of similar difficulty. Ideally, they're all roughly the same. And just to mention a bit of the idea here is because let's say you have just 2 cases that you're solving in parallel. Well, if one concentrates all the difficulty, then the easy one will be done, and then you'll end up spending all your time in the hard one. So hopefully you divide your problem into similarly difficult cases. So in our previous work of 2022, we did a split directly over the direct variables. So our cases were looking like, okay, imagine a case where vertex 4,3 gets color 5, vertex 9,0 gets color 13, and vertex 3,3 does not get color 7. So that's a possible case. And the idea is that by assuming these facts about a solution, it will be easier to discard that it could potentially work, because we're already assuming certain things. In this work, we do our split over the auxiliary variables that the plus encoding introduces, so the y variables I mentioned earlier. And let me tell you why that's actually a much better idea. So in the old way of splitting in terms of the direct variables, if you have the variable x on the vertex 4,3 and color 5, when you split it into cases, you're basically sort of dividing the world on whether that's true or not. if that's true, if that vertex gets indeed color 5, then you actually did a lot of progress. That's like finding a number in a Sudoku, right? When you find the right number, that is a lot of progress. The problem is that if you say that no, that color does not get color 5, then that's actually not a lot of information. It's not helping you much. So that case gets very hard. It's like saying in a Sudoku that that cell does not get color 7. And that's like, sure, but it's not super helpful. The advantage of the auxiliary variables that represent regions is that if they're positive, then you know that somebody in that region gets color 7. And that's pretty useful. It's less useful than knowing exactly which vertex gets color 7, but it's still useful because it's a small region of the space. It's only 5 vertices as it's a plus symbol. And then if it's negative, now you do get a bit more, because now you're saying that nobody in that region gets color 7. So you're discarding it from an entire region. So you're discarding it from 5 vertices, and that's significantly better. So it's a more balanced way of designing cases. And as I was saying earlier, balanced is the trick for parallelism. So what we get out of doing this right, it's actually linear speedups. So if sequentially we manage to do that in 800 seconds by using 128 cores in a good computer, we reduce the search to 6 seconds. So that's a factor of 123, which is pretty similar to a number of cores. That's basically the heaven of parallelism. Get a speed up that's just proportional to the number of cores you're using. Another contribution of our work is what we call the at least one distance clauses. So the idea here is the following. Every D1 subgraph must contain a 1, or so the solution I have displayed here does not have the allowed clauses, the at least one distance clauses. When we enforce them, notice what happens. The 4 that I had there gets turned into a 1, because these clauses are forcing that in every sub D1, so in particular, it could be the D1 center on this 4, even though part of it gets outside of the graph, but I can still think of it. I'm enforcing that it must contain a 1. And the reason why I can enforce this without losing generality is because if I was going to have a D1 that does not have a 1, then there's no conflict in changing its center to a 1. And given that smaller colors are the ones that introduce the fewest conflicts, as soon as I can change something for a smaller color, then I might as well do it because I'm winning something. So also benefit of doing this is that the solutions get more structured, as this picture is saying. So I explained the reason for correctness, and it's hard to formalize what it means that the solution gets more structured, but we do measure this empirically, and we get around, if I remember correctly, a 20-something% speed up by including this form of restrictions. So here's a bit of an ablation study running on a single core, and we can see what the impact of each thing is. This was on for proving a lower bound of 12. So if you don't do any of these things, a modern SAT solver will do it in 10,000 seconds. So that's roughly 3 hours. With these things on a single core, it gets down to 55 seconds. And once you do cube and conquer, you can solve this one in less than a second. For reference, this same study is what is enough to prove a lower bound of 12, which when originally done took 120 days of computation with a simulated annealing algorithm. Now we can do that in less than a second. So I'm approaching, I guess, the end. Let me talk about how do we prove that all of our ideas are correct, the cube and conquer, the symmetry breaking, and so on. So we use several ingredients. We use this particular subgraph, a color in the center, the plus encoding, symmetry breaking, 5 layers of it. cube and conquer with over 5 million cubes and a particular algorithm that we devised to do the split, these allowed clauses, and so on. So with all of that, we end up getting the final result, the lower bound of 15, which closes the problem because we had already an upper bound of 15. And that took almost 5,000 CPU hours. So that's less than 2 days on 128 cores. The DRAD proof, so that's a proof format, it's 34 terabytes long. And that's compressed from an LRAD proof that's actually 122 terabytes long. So this is a pretty long mathematical proof, if you will. It's not the largest, though. So in order to generate this proof, what we do is to basically prove the correctness of each of the ingredients of our solution individually, stitch them together in the appropriate order. And so for example, the correctness of the allowed clauses come from these clauses being blocked, which is a notion in propositional logic that implies that you can add them to a formula without reducing the number of solutions. We need to prove that our splitting cases is a tautology, right? And proving that something is a tautology, it's also a co-MP hard problem. So we use obviously that solver to do that. And we implemented a prototype to prove the correctness of our symmetry breaking in the DRAD proof format. So at the end, the only unverified core of our whole thing is the direct encoding, because the translation from the direct encoding to the plus encoding is itself verified. So all you need to do is to prove that I guess, trust that the direct encoding represents faithfully the mathematical problem. But that's actually a very simple encoding, as I showed earlier, and we put in the paper an implementation that's only 26 lines of Python code. And then for completeness, after the paper is done, we verified that the Python code is correct in cake in a theorem prover. So now even that part is verified. So we end up with a single unified DRAD proof that can be independently checked by any computer, and that fully implies that the packing chromatic number of the infinite grid is at most, it's at least 15. So the proof is for at least 15. We already knew that it was at most 15 because there was a solution with 15 colors. So that's basically the core message I wanted to give, just the different ingredients and sort of tools we were using. But now, if I still have a few minutes, I would like to just show some cool things that I just found fun while working on this. So I'll do that very quickly, and then we can go for questions and a discussion. So a first thing is that Donald Knuth, so one of I guess my heroes in computer science, is very interested in the combination of, in the intersection, I guess, of set solving and graph coloring. And so we sent him a copy of our paper after we were done, and he read it and gave us some feedback, which to me was pretty amazing. But something cool that happened because of that is that he told us that the plus encoding reminded him of the tiling on a church in Roa, a city in Norway, that his wife and him visited in the 1970s. And we managed to find a solution, sorry, it's not a solution. We managed to find a picture of that cathedral online in a Norwegian website. And it is basically a structure plus tiling, which is pretty cool. So we sent him the picture back, and he just sent us a one-line email saying that the internet is wonderful. So another thing that I'm quite excited about is something that we call the chessboard conjecture, and it goes like follows. So before we manage to actually put all the ingredients together and finish solving the problem, we consider the following idea. It's like, can we assume that the color 1 will be used like so in a chessboard pattern? That's why we call it a chessboard conjecture. So the question is whether you can assume this without loss of generality. And if so, then that gives you a dramatical performance speedup. Why? Because then you know already what color half of the graph gets. And given that these problems are of exponential difficulty, reducing the input by half is like a massive gain. And actually, we proved before we had our full result that if the Chesbrough conjecture was true, then that was enough for everything. Because it was not too hard to prove that the formula of the 14 diamond with 14 colors, assuming the Chesbrough pattern and a 6 in the center, was unsatisfiable and therefore impossible to do. So we already have that. And then what we were trying to do is like, okay, let's just try to prove by hand the Chesbrough conjecture, and then we'll be done with this and, move on to other problems. But it turns out that the conjecture is actually false. And we found the smallest counterexample after we were done with the main result. And this is the smallest counterexample. So it is over D14. There's no, if you think any smaller than radius 14, the Chesbrough conjecture always holds, meaning that whenever there is a solution, you can assume the Chesbrough pattern. But for 14, you actually cannot. So let's see what's happening. I'm removing everything that's not a 1 from the picture for you to be able to see it more clearly. And if you pay attention in this very border on the left, there are actually 2 ones that are out of the Chesbrough pattern. And weirdly enough, deviating by that amount is enough to have a solution when you consider the diamond of radius 14. When you consider the diamond of radius 15, then there's no solution. That's how we got our final result. But with the diamond of radius 14, it's unsatisfiable if you use the chessboard. But if you don't use the chessboard, it manages to find a solution that almost uses the entire chessboard pattern, except that it deviates on 2 vertices. So my advisor and I like this counterexample so much that we made some art with it from collaborating with a design company. So we each got this sort of paintings in metal of the counterexample. And now, finally, the last fun thing is that for the upper bound of 15 had already been shown by Martin and others in 2017. And the way they did it was to take a previous known solution with 16 colors, and they managed to, do some clever changes to argue that actually you didn't need the 16th color, but 15 was enough. We reproved the result using a local search solver. So our result only is fully automated, and it uses a toroidal 72 by 72 grid. So a grid that we connect sort of in this toroidal manner I was describing earlier, plus assuming a chessboard, plus assuming a 6 in the center. So an open question, if anyone wants to have fun, is whether it's possible to find a periodic packing coloring that uses a smaller tile size than we did, so smaller than 72 by 72. Because we also tried, let's say, 48 by 48, and we just couldn't get it, but it might exist. So here is the actual last thing, and I promise I'll shut up after this. But David Scali from, if I'm not wrong, Hungary, made a really cool animation of the upper bound solution we found with the set solver. So I just want to show you guys that animation. So it's sort of using these pancake stacks, I guess I want to call them, to represent that different colors have different heights. And that part of the reason why I really like this animation is that it's reminiscent of the broadcast coloring idea that introduced this whole world of packing colorings back in 2002, where they were thinking about modeling radio stations, some of which are more powerful than others, and the most powerful ones need to have a bigger radius in which they cannot have interference with other using the same broadcast frequency. Whereas if you're a very small radio, maybe you can have the same broadcast frequency not too far away from you. So that's it. And I'm now really excited to take questions or just discuss fun things.
Bernardo, that was excellent. Thank you so much. Since there's such a small crowd, I think people can just kind of freely jump in and ask questions, but maybe I'll get us started with one. Have you thought at all about how the problem changes when you snip an edge, or when you snip infinitely many edges in a pattern? For example, if I go in with a pair of scissors and I cut every third edge in a line or something like that. I mean, there's all sorts of ways you could formalize that problem. I'd be curious if you've thought about that at all.
Right. So I've thought about it a little bit. So given the audience is small, they can confess something. So we started working this problem before knowing all its history and that people had like thought about it and did some results. So we actually sort of reinvented the wheels a few times before doing this. So we also studied other infinite graphs. Like what if, for example, instead of having only orthogonal neighbors, you have also diagonal neighbors, for example? Or what if instead of being Z2, the problem takes place over Z3, right? So it's like this sort of infinite cube. And for each of those, you'll get different answers. We also thought about like infinite binary trees, for example, and so on. So getting more specific about your question, I never thought about exactly what you're mentioning, which is quite interesting. So taking still the 2D infinite grid, but sort of cutting things and seeing if then you can suddenly do 14, for example. Like a cool question that pops into my mind is like, okay, if you remove just one edge, you'll probably not be able to use only 14 colors. How many edges do you need to remove at minimum to be able to use 14 colors? And the answer is going to be obviously infinite, but I mean by density, right? So what proportion of the edges will you have to delete in order for this to be solvable with 14 colors? I have no idea what the answer is, and I think it's quite an interesting question. So
Yeah,
thank you.
I wonder if there's some way that having theorems about cutting edges could get you to having theorems linking aperiodic to periodic solutions, right? Because if you can do a true cut that genuinely splits the entire infinite graph into two parts and have equisatisfiability, then now you have a tool you can start to use to maybe, chop out like a finite part, and then maybe you can make some sort of periodic argument. I'm really speculating. I don't know, but
No, yeah, that sounds super interesting, honestly. Yeah, and I'm really puzzled by this question of the periodicity. So yeah, let us grab more questions if there are, and otherwise I can give more details on that question or
Lewis and Jake, if either of you have anything, you should just go ahead and jump in. But if not, no worries. Yeah.
so there's one, maybe if we, I don't know if we have time, but there's one thing, given its small audience that I would love to share, is that there's a really cute proof of why no finite amount of colors works if you consider the graph with diagonal edges as well. So each node having 8 neighbors instead of 4. So if there are no questions, maybe we can do that and then close because it really takes a minute. So sorry,
Perfect.
I'll go to Zoom. How do I? Oh yeah. So I'll sure, we'll whiteboard. So what I was suggesting is what if we sort of sorry, think of it with nodes having diagonal neighbors as well. So it would look sort of like so. So these guys are all connected. And obviously I'm just drawing a finite part of this, but hopefully the idea makes sense. And you continue like so. So it actually turns out that the packing chromatic number here, so I'm just gonna write it as PC to not write math, is actually infinite. You cannot color this infinite graph with a finite amount of colors. The proof is really, really surprisingly cute. So if we look at this 3x3 graph, I could place a 4 here. Let's say I place a 4 over there. Can I place another 4? Question for the audience. Yes, no? Could I place another 4 in this 3x3?
Everything's 2 away.
Right, so I could not place a 4 anywhere. And that's implying something. It's implying that I can have at most 1 4 in this graph, right? And that's at least telling me that every 9 vertices, I can have at most 1 4. So that's telling me that the density of 4 needs to be smaller or equal than 1 over 9. Because I look at this 9 vertices and I can have at most 1 4. I look at the next 9. So I split my infinite grid into this little 3x3 ones. And 4 can only appear once in each of those. So in total, it can only appear with the density of at most 1 over 9. So more in general, if you have color K, and you imagine that you split the infinite grid in this square chunks of side K, so there are K edges on the side, then this guy here and this guy here are a distance K, right? Because you can take the diagonal edges now. So that's, so the maximum distance here, I guess, is K, which means that you can only have the number K in this K by K square at most once. If you had it somewhere else, then there would be a distance smaller than K, which would break the rules. So this gives us an upper bound on the density of color K. In particular, is telling us that it cannot appear more than, actually can do something slightly better than what I said and do K plus 1 square. Because if my square is of side K plus 1, still the largest, well, I guess it depends on what we mean by side, but if I'm talking about the number of vertices, then it's K plus 1 vertices, because the distance is K. So that means that the density of color K is at most 1 over K plus 1 square. And if I sum that density over all K starting from 1, that's the same as, or that's smaller or equal than doing the sum of that thing, right? So 1 over K plus 1 square. And you can sort of translate that sum to be the sum of 1 over K square, and then subtract the first term, which would be 1. But the sum of 1 over K square is actually the problem that Euler solved, and it's P square over 6. And because of the -1, we get that the sort of sum of these densities is pi square over 6 minus 1. And this number turns out to be smaller than 1. So the sum of our densities is smaller than 1, which means that we have not been able to cover the entire graph. And therefore, it's not possible to color this with a finite amount of colors. So it's a really cute argument, in my opinion. And it's really nice that this sort of infinite sum that's equal to pi square over 6 apiers.
That's super cool. That's a beautiful proof.
Yeah, I really like it. It was a sad moment when we realized that our people had done it earlier, but that's okay.
Bernardo, this was terrific. Thank you so much. I think this was a really visually elegant talk and a fascinating problem. And I'm going to be thinking about taking scissors to infinite grids for the next 48 hours. So,
Yeah, no, yeah, and I would love to chat offline after this at some point on the periodicity thing because I'm actually quite curious and I would love to know. So
yeah, absolutely. That'd be great. Well, cool. And it's okay, just to be clear, if I post this video online, right? So people can watch it, or do you prefer it's only available to group members like in our private Slack?
no, it's totally fine. Yeah. Yeah. And I assume, I guess, like, oh yeah, I guess you started recording after like or when we were starting. Yeah. No, it's totally fine.
Okay, sounds good. Bernardo, oh, sorry, go ahead.
I was just gonna say, that was really well explained in plain English. I'm one of Max's old roommates from undergrad, so it's not that I have no math background, but it's been a few years since I've done a math class, and I didn't really have any trouble, understanding what you were getting at there. So yeah, good use of kind of breaking it down in plain English, and as Max said, the animations. So
Justin's too humble. He got straight A's in real analysis.
No, thank you. I love that.
This is great. Thank you so much. It was a lot of fun.
Thank you. Thanks, everyone.
Bye.
Bye.